it's all about writing properties from the specification and maybe doing some protocol compliance check on some modules before starting the verification. And this is indeed a very powerful method that you can use, but we are beyond this because these days Jasper has leveraged the formal verification so much that we are able to address different problems throughout the design cycles, and this presentation is about to give you an idea where and how our customers are using Jasper to solve their verification problems. So for those of you who don't know Jasper, Jasper is a supplier of verification solutions based on formal technology. Our users span from architects to designers to verification engineers through also silicon bring-up teams. And our customers base is very broad. I've mentioned just a few customers of ours like ARM, Intel, AMD, Qualcomm, Broadcom, Ericsson, just to mention some of them. Mike has already mentioned this morning. One of our customers, ARM, has introduced this sort of, let's say, buzzword, to sort of synthesize different or to reference different deployment models that they are using with Formal in their design flow. And the word stands for bug avoidance, bug hunting, bug absence, and bug analysis. I think Harry mentioned this morning that if you want high quality, you shouldn't basically put bugs to begin with in your design. And this is what the first stage, bug avoidance, tries to do, which is also called the design bring-up, which basically they try to use the Formal as an aid for the design to come up with to catch bugs earlier in the design cycle, and also to provide higher quality for the module that will be passed to other teams or design teams or verification teams. The second one is bug hunting. Here you are focusing on finding bugs both at module levels but also at top level. And it's important to mention that here there is no effort for proof. So you are not looking to prove your properties. You just want to go deeper and see if you can hit bugs. The third is about bug absence. Here people with verification or with formal skills are involved because it's about making sure that your design is working as expected, or to be more precise, that a certain functionality or critical functionality in your design needs to be verified 100%. And here, again, this step may require considerable user expertise and also effort. And then the last one, bug analysis, it's about investigating late bugs. Obviously, you need to isolate those corner cases bugs, because if those bugs escape to silicon, that means that your verification environment has missed those, so you need to somehow first reproduce those and then to use the same environment to confirm the fix. And yet, even though there are customers like ARM that I mentioned, there is still a perception about Formal as being a point tool that people need a PhD to use it, that you need to write a lot of properties, that you can only apply it on a very small module. And actually, what this perception is not justified, because what is really possible with the Formal using Jasper is really addressing several problems during entire design cycles that I'm going through in coming next. The first one is the normal, let's say normal formal property verification, where you apply formal on-target blocks where you know that your return on investment will be maximized as opposed to a simulation, which means that probably there is a lot of control logic in that module, and simulation doesn't provide the necessary coverage for this. X-propagation has been mentioned also in one of the presentations before. It's also another problem. System-on-chip integration, this is also something that has come up repeatedly during the previous presentation. Here I just mentioned connectivity verification, where you want to make sure that your RTL really implements the connectivity definition that you have. CSR verification, the automated register verification, or there are other system-on-chip related applications like glitch detection or multi-cycle path verification, and also one which is very compelling currently, which is low power verification. And there are also other applications that are not in these slides, but we are working with a few customers to develop them, like the security and the deadlock, just to mention a couple of them. So basically, again, the idea is that talking to customer and seeing basically what's their problem, this led us to basically develop all these applications that like executable spec, RTL development, and also the architectural modeling, intelligent proof kit. I'm going a bit fast, otherwise the timing will. So all these applications are targeting really problems throughout the entire design cycle. So starting from the architectural modeling, which is a very high-level view, until the post-silicon debugging. And now I'd like to go a bit more deeper in a few of the applications, just to give you an idea how this works in a bit more, let's say, details. So the first one is the RTL development, which is basically to connect to the first A that we have seen, the bug avoidance. If you want to hit a particular state or condition in your RTL and you are using simulation for it, you need to come up with a test bench that applies an input sequence that will bring the design in that state or that will hit that condition. So if you want, by using simulation to perform such an operation, it's more of an input-driven method. Jasper has a feature which is called visualize feature that enables the user to specify really a state or a condition, which we call a target, and then basically the tool figure out a trace starting from the reset state or a state that the user has provided, and will hit that particular state or a condition. So this is more really an output-driven method. And this allows basically the designer to start writing simple cover or simple, how we call them, behaviors about the design, to group those covers or behaviors in more complex behaviors, and then from those, eventually you'll write or you'll extract assertions that will then be used for other, let's say, flaws either in the design or in the verification. To make it even more, let's say, clear, you start from the RTL and you visualize some behavior by doing what-if analysis, and then you combine and save those scenarios in a in a database. If you like what you are seeing, you move on and you modify your RTL, maybe implementing a new feature or other things like that. And at this point, once you are done with the modified RTL, you will check that the what you have saved in the database is still true in your modified RTL. And if it's not, obviously you need to debug. And by doing this this cycle, you basically come up with a not only with your design, but also with the corresponding assertions that are supposed to verify your design. So basically, this allows you to conduct early RTL exploration, to store the expected functional scenarios, and also, as I said, the properties that are developed at this stage will be passed on to the verification team, for example, to be used either in simulation or statically informal. The next one is X-Propagation. We can have different sources of X's, like non-resettable flop. Resetting flops is becoming more and more expensive. For example, you want to have some, for some reason that you want to control or inject X's in your design for the inputs, or you have explicit X assignment in your RTL, and you cannot rely on simulation to perform those checks because simulation is not exhaustive, and on top of that, it doesn't use the same semantic that is used at the gate level. Instead, formal can be used, and there is the dollar is a known construct of SVA that allows you to use X's in your verification. So again, you can check X-propagation, or whether you can check exhaustively whether one X can propagate to a target signal by using formally optimized engines. Another thing that we mentioned is system-on-chip integration. And here you can have a whole bunch of applications that you can use Jasper for, starting with the automated register verification. Here you have basically a design which has a standard interface, or sometimes even a proprietary. It really depends. And you want to basically prove properties or end-to-end properties, like that the value that you are reading out of a register is matching the one that has been updated previously. And this is done by defining or by capturing in the register definition either spreadsheet CSV format or IP exact format. You will basically configure the register and also the field. You can have a comprehensive range of behaviors that you can capture also, fields in the registers or access types like read and set to one, read write, all those kind of accesses. And there is also the chip level connectivity verification, which is quite straightforward. You have a connectivity map which specifies the kind of connections which can be structural. For example, 2 points are just equivalent, could be conditional. The 2 points are only connected when the condition is true, or you can have also a temporal expression, which means that there is a certain delay in the connection. And again here, once you load the connectivity map into the design, you can see that the assertions are automatically created. So the user doesn't even know that he's using formal to perform this task. And if there is a problem, obviously you'll get a counterexample, which is basically a trace that shows one possible case where it's not true that the two signals are connected. So a summary of the system integration is that there are a lot of areas that can be automated, like the CSR or also the glitch detection to verify that there are no clock glitches, and and other things. And the point that I want to stress here is that, as I mentioned, for the connectivity check, the technology that is used behind or that is used by the tool is really irrelevant to the user. It's more really the automation of the task that needs to be performed that is that matters. Another area is the property synthesis, where you basically can use Jasper to synthesize properties either from your design or from your design plus the simulation data. And the reason why you want to do this, well, there are several ones. You may want to increase assertion density, because assertion density helps you to find problems quicker if you have a long trace and you find that there's a problem. And there are two kinds of properties that can be synthesized. The first one, which is called structural properties, where you only need the RTL, no test bench is required, and the set of properties which will be created that can be used either right away, or that you can use Jasper to prove, or that you can export and use them in either later stages or even in simulation. Or you can synthesize what we call behavioral properties, and here you require also simulation, or the tool requires simulation data that will be used in order to extract properties. And that is typically used in later stages of verification. Structural property synthesis, some of them out-of-range indexing, arithmetic overflow, or FSM checks, or stacked signal. Behavioral property, as I said, you need simulation data, so you feed in either through the BCD or FSDB files, or through the PLI interface to the simulator. You feed in data, and the tool will come up with the constraints, assert, or covers, and you can export those and use them either statically in formal or in simulation. So the property synthesis summary properties, this can be used either at early stage during the design to discover, let's say, problems that are relatively simple by using the structural property synthesis, or can be used at later stages of the design using the behavioral approach in order to synthesize interesting properties, to raise the assertion density, or also to discover holes in your or coverage holes in your test bench. So the conclusion is that Formal has been expanded a lot over the years. We have been working together with the customer, focusing on problems and not on the technology. So not just saying this is our tool, just use it. But we have been good listeners to really see what were the verification pain that the customer had, and eventually all those problems led to our suite of applications. And as I said, also many other applications are coming up as we discover more and more verification pains that the customer has. Therefore, as also Yannick said, if you have a verification problem or any kind of problem, just come to us. We'll be happy to help if we can. Yeah, that's it.